This is the screencast for section 2.6, example 5. We're going to analyze graphs of rational functions. Now you've done this about 1,000,000 times so far, but maybe in this round of analyzing rational functions, you'll make a few connections that you didn't before. Maybe you've always wondered why that happened. Well, hopefully we can answer all those questions for you. And by we, I mean me. Alright, so first I'm going to factor out. So I've got x minus 1 in the numerator over x, minus 3 times x plus 2 in the denominator. So right off the bat I can tell you that the domain is going to be negative infinity to negative 2, negative 2 to 3, and then 3 to infinity, because both positive 3 and negative 2 make the denominator 0, so they would cause an error. There are going to be, discontinuities, interesting. There are going to be 2 discontinuities then at negative 2 and 3. They're both infinite because positive 3 and negative 2 only make the denominator 0. I can test symmetry without even knowing what the graph looks like by plugging in a negative x. So I didn't get the exact same thing that I started with, nor did I get the exact opposite, so the symmetry is neither. What else? Asymptotes. I know that there's going to be a vertical asymptote at, both infinite discontinuities. So that's x equals 3 and x equals negative 2. Then there's going to be a horizontal asymptote. Now the degree in the denominator is higher, so there's going to be a horizontal asymptote at y equals 0. And then I can find my x and y intercepts. I set the numerator equal to 0 because when 0 divided by anything is 0. So an output of 0 will be achieved when x equals 1. So my x-intercept is 1, 0. My y-intercept is when the x value equals 0. So my y-intercept, after I plugged in 0 for x, was 1/6. So now I have a pretty accurate graph, at least the beginnings of a very accurate graph. I'm going to sketch all the information I know first. So I've marked my vertical asymptotes, my x-intercept, my y-intercept, my horizontal asymptotes, and I'm going to use my calculator to kind of check all that information. The first piece of this function is going to come away from the horizontal asymptote at y equals 0 and then approach the vertical asymptote at x equals negative 2. The next piece, by looking at my calculator, that's all decreasing, so that's going to come down from positive infinity at the vertical asymptote x equals negative 2, hit the y-intercept, hit the x-intercept, and then approach the other vertical asymptote at x equals 3. Then the last piece is decreasing and above the x-axis, so we're going to come down from the down from infinity at the vertical asymptote x equals 3, and then approach the horizontal asymptote at y equals 0. Now I can answer the rest of these questions. My range is going to be negative infinity to positive infinity. There are no y values being left out of this graph. I have a horizontal asymptote, but the middle part does use up the y value 0. So 0 doesn't get left out. There aren't any removable discontinuities, so all real numbers are being used for the y values in this function. Extrema. This graph is always decreasing. It never changes from decreasing to increasing, so there are no extrema. So in other words, speaking of decreasing, it is decreasing from negative infinity to the vertical asymptote at negative 2, then from, negative 2 to the other vertical asymptote at 3, then from the vertical asymptote at 3 all the way out to positive infinity. The function is unbounded. It goes all the way up to positive infinity and all the way down to negative infinity, so unbounded. Now, where are the f of x values greater than 0? So in other words, where are the y values greater than 0? Well, that occurs from the vertical asymptote until the x-intercept. So from negative 2 to 1, and it doesn't include 1 because 1 is where the graph does not, 1 is where the graph equals 0. I'm just asking for greater than 0. Then again, after the other vertical asymptote, all the way out to infinity, the graph is above the x-axis, therefore the y values are positive. So I'm going to put and, that would be 3 to infinity. So then where's the graph below the x-axis, or where are the y values negative? Well, that would be from negative infinity to the vertical asymptote, -2. Then again, in this little chunk after the x-intercept up to the vertical asymptote. So that would be from, let's see, 1 to 3. So we're using interval notation just like we would increasing and decreasing. It's just now I'm asking you where the graph is above the x-axis and where the graph is below the x-axis. Now we have 6 end behaviors to describe. First, I'll describe the end behaviors associated with the horizontal asymptote. So the limit as x approaches negative infinity of f of x is 0. As we go out to the left on the x-axis into negative infinity, the y values approach 0. Then out to the right, same thing. The limit of f of x as x approaches positive infinity, so to the right on the x-axis, the y values or the f of x values are also going to approach 0. So there's 2. Now let's look at the vertical asymptote at x equals -2. Well, the limit of f of x as x approaches -2 from the left. So coming in from the left at this vertical asymptote, coming in from the left, the y values go down to negative infinity. Coming in from the right, so the limit of f of x as x approaches -2 from the right, those y values go up to positive infinity. Last but not least, this other vertical asymptote, the limit as x approaches 3 from the left, so coming in from the left, those y values go all the way down to negative infinity. The limit of the f of x values as x approaches 3 from the right, so coming in from the right, the y values go up to positive infinity. The now try problem for example 5 is number 39. So we're going to, I know the directions say find the intercepts, asymptotes, use limits, vertical asymptotes, analyze, We're going to do everything because it says analyze and draw the graph. So we're going to analyze it like crazy. So first, factoring out. So I have x minus 1 in the numerator. In the denominator, let's see, x minus 4 times x plus 3 would multiply out to be x squared minus x minus 12. So that means -3 and +4 need to be left out of my domain. Since +4 and -3 only make the denominator 0, they are both vertical asymptotes and also infinite discontinuities. Speaking of asymptotes, the degree in the denominator is higher than the numerator, so the horizontal asymptote is y equals 0. I can test for symmetry by plugging in f of -x or plugging in -x to the f function. Since I didn't see, I don't get exactly the same thing or the exact opposite as I started with, my symmetry is neither. I can also algebraically find my x and y intercepts. The x-intercept is 1, 0. The y-intercept is 0, -1/12. 1, 0 will lie on the x-axis. The 0, -1/12 will lie on the y-axis. So those are the x and y intercepts. Now I'm going to use the information I've gathered so far to help me create some details in my graph, so my sketch will be pretty accurate. So I've sketched my 2 vertical asymptotes, my x and y intercept, my horizontal asymptote, and now I'm going to graph on my calculator to make sure that everything I've got so far works with what the calculator is predicting. And it looks like it does. So now I need to sketch the rest of the graph, making sure that the pieces approach the asymptotes as predicted by my algebraic work. So now that my sketch looks like what my calculator produced, plus all the accuracy of the work I did, I can use the graph to analyze the rest of the function, or characteristics of the function. The range is going to be -infinity to infinity. There are no y values being left out of this function. No holes, no asymptotes. Actually, there is a horizontal asymptote, but the middle of the function goes through it. So 0 as a y value is being used. So the range is all real numbers. The graph is always decreasing, so there are no extrema. Since the graph is always decreasing, it is decreasing from -infinity to the left asymptote at -3. then from that asymptote to the other asymptote at positive 4, and then from that asymptote all the way out to positive infinity. The function is unbounded, goes all the way up and down to positive and negative infinity. The part of the function that is greater than 0, the y values that are greater than 0 or above the x-axis, take place here. So from the vertical asymptote at negative 3 to the x-intercept at positive 1, and then again after the other vertical asymptote at 4 all the way out to infinity. Those are the pieces of the x-axis that produce positive y values. Now the pieces of the x-axis that produce negative y values, well, the function would be below the x-axis because that's where you plot negative y values. Let's see, that would be from negative infinity until the vertical asymptote at negative 3. Then after the x-intercept all the way to the other vertical asymptote, so that would be from 1 to 4. There are 6 end behaviors to describe. The end behaviors for the horizontal asymptote, as x approaches both positive and negative infinity, the y values will also approach 0. The left vertical asymptote is at the value x equals negative 3. As x approaches negative 3 from the left, the y values are going to go down to negative infinity. But as x approaches negative 3 from the right, the y values are going to go to positive infinity. Now, if you haven't noticed, I've been switching some of these f of x's to h of x's. I've been saying f of x, but this function's called h of x. I need to identify it by its proper name, and I noticed that after the fact. So I switched all my f of x's to h of x's, and I'm going to continue to use h of x. So the other end behavior that I need to describe the asymptotes are occur where x equals positive 4, this vertical asymptote. As x approaches 4 from the right, the y values go up to positive infinity. But as the function approaches 4 from the left, the y values go down to negative infinity.